In this class, I will explain how to derive the discharge equation for a small orifice which is discharging free and also sharp edged. So last class I had explained about different types of orifices. So in that the important thing is here I am taking a sharp edged small discharging free orifice. Let us see how we can find the velocity and also discharge for that type of orifice. So this is the diagram for the derivation. So this is the tank, so to which this orifice an opening is made here. So this is the orifice. It can be of any shape, rectangular, triangular, circular, square, whatever it is. H is the head of this orifice, which is measured from the center of the opening to the free surface. This is the free surface. And the jet of water, you can see here, it emerges out like this. So it is discharging free because the jet is subjected to atmospheric pressure, and it is a small orifice because the thing is, I have taken H greater than 5 times D. So this is the condition for small orifice. So these are the notations. A0 is the cross sectional area of the orifice. If it is a circular orifice, it is pi d square by 4. If it is rectangular orifice, it is B into D like that. A is the head over the orifice. Q is the discharge of this jet or rate of flow. So these are the units. A should be in meter square, H should be in meters, Q should be in meter cube per second. Gamma is the specific weight of the liquid which is contained here. So normally we take water, so gamma will be 9810 if it is water, Newton per meter cube. So I will take 2 points here, one within the tank and another one here in the jet. So this I will take it as 1 and 2. Here this 2 is there, section 2. The section 2 is called as vena contracta. Very important. The characteristic of this vena contracta is at this point, the area of the jet will be minimum. So area of jet is minimum and velocity is maximum. That means V2 is maximum velocity. So V1 is the velocity here, V2 is the velocity here, P1 is the pressure here, P2 is the pressure here. Z1 and Z2 they are the determinants at the 2 points. Now if I take this line itself as the datum or reference line, then both Z1 and Z2 will be 0. And if you assume losses as 0, because we are deriving the theoretical equation of velocity, I will take losses as 0, so then HL will be 0. So in this case, see here Z1 and Z2 they will be 0. Assuming no losses, HL also will be 0. Now we are going to apply Bernoulli's equation. So all these equations are derived from the Bernoulli's equation. At the sections 1 and 2, I will apply the Bernoulli's equation. You know that the total head remains constant. So total head consists of 3 terms, P1 by gamma plus V1 square by 2G plus Z1 for at the section 1 or at point 1. At point 2, total head is P2 by gamma plus V2 square by 2G plus Z2, of course plus HL. Now according to our assumptions, so by taking the center line of the orifice as itself as the datum, you will get both Z1 and Z2 is equal to 0, and assuming no losses, HL will be 0. So this equation reduces to this form. Then from the diagram you can see that the pressure head at 1, the pressure at 1 is nothing but P1 by gamma, and that will be equal to H, because pressure head is nothing but the vertical distance of that point from the free surface. So that is H here, capital H. So P1 by gamma is capital H. P2 by gamma is taken as 0 because it is atmospheric. So P2 is atmospheric. That's why normally what you do when you are writing the gauge pressure, atmospheric pressure is taken as a reference. So therefore it is taken as 0. Then if you see here, velocity is maximum at 2. I have already told because area is minimum, velocity is maximum. So this value of V1 will be very, very small when compared to V2. V2 is the highest value, maximum velocity value. V1 will be very, very small when compared to V2. So the flow will be here very slow. So in that case, what you can do here, the assumption is V1 you can take it as 0 because V1 is very, very, very small, smaller than to V2. therefore V1 can be taken as 0. Now, if you substitute these things here, P1 by gamma is H here, this is neglected, so this becomes 0. And here P2 is atmospheric, therefore it is taken as 0. Then V2 square by 2g will be there. So only you will get this as H, this as V2 square by 2g. So this is the equation. Or V2 is equal to V2 square is equal to 2gh, or V2 is equal to root 2gh. So you please note that this V2 is nothing but your Vmax, maximum velocity, which you are going to get it as root 2gh. So just by knowing the value of this H, that is the head over the orifice, you can compute the theoretical velocity. This is theoretical velocity because we have not considered losses. When HL is equal to 0, you are going to get the theoretical values. So this is theoretical velocity of the jet. Now, actually, we have to measure the actual discharge. So actual discharge, why? Because there will be some losses during the flow that should be accounted for. So for getting the actual discharge, we have to get the actual velocity. So this is the theoretical velocity at Vena contracta. Now actual velocity will be obtained as by multiplying this theoretical velocity by a coefficient called coefficient of velocity, which is less than 1. So that means VA is equal to CV into root 2gh. So like this, VA is equal to CV into root ph. So the same thing I have used in the case of pitot tube also in the last class. So CV is called as the coefficient of velocity. Now once you get the value of VA, then your QA, actual discharge, is given by A into VA. Please note that here A is cross section of jet at Vena contracta. So this area is different. Please note that this area is A0. Area of orifice is A0, whereas area of jet at Vena contracta, this one is A. So when you want to actual discharge, that area of jet at Vena contracta multiplied by actual velocity, so that you will get the value of actual discharge. So actual discharge through a orifice is given by A into VA, where A is the area of jet at Vena contracta and VA is the actual velocity, or it is called as the velocity of jet at Vena contracta. Then you will get Q actual. Now there are three important coefficients, hydraulic coefficients. This is also an important question. So define the hydraulic coefficients of an orifice and obtain the relationship between them. So the three coefficients of an orifice can be written like this. First one is the coefficient of discharge, CD, which is defined as actual ratio of actual discharge to theoretical discharge. So this is the general definition in all the devices. When you take the ratio of actual discharge to theoretical discharge, it is called as coefficient of discharge. In any flow measuring device, so if you take the ratio, this ratio it is called as coefficient of discharge. Second one is coefficient of velocity. Similarly, this is ratio of actual velocity to theoretical velocity. Please note that actual velocity is calculated by taking losses. Theoretical velocity is calculated without taking losses. Now CC is the coefficient of contraction, which is defined as area of jet at Vena contracta divided by area of orifice. So A divided by A0. So these are the definitions of the hydraulic coefficients. Now we will see how we can get the relationship between them. So you have the definition of CD as QA by QT. This QA is nothing but, as per the definition, it is QA is A into VA that I have written. QT is A0 into VT. That means you have to take the area of orifice multiplied by theoretical velocity, use the theoretical discharge. Now if you separate them, A by A0 I will take separately, VA by V0 I will take separately. A by A0 is nothing but CC, VA by VT is nothing but CV. You can see here. So VA by VT is equal to CV, or you can say here also. So that means you got CD is equal to CC into CV. So this is a very important relation between the hydraulic coefficients of an orifice. By knowing any two, you can find out the third one using this equation. Now the values, normal values of CD, CC, CV are like this. CV 0.95 to 0.99, CC 0.61 to 0.69, CD 0.61 to 0.65. Please observe that. So these coefficients give an idea about the losses. So here the value of CV is high. So that means the loss in the case of velocity is slightly less, whereas in the case of discharge the losses are high because of the coefficient of contraction. So you have to remember the standard values. Now there is one more coefficient that can be defined called coefficient of resistance, CR, which is defined as the ratio of loss of kinetic energy per unit weight to the actual kinetic energy per unit weight, or you can also write it as loss of kinetic head. You can write it as loss of kinetic head divided by actual kinetic head. So actual kinetic head. So like you can define CR like this, actual kinetic head. So loss means, once again, it is the difference between the theoretical value and the actual value. So theoretical kinetic energy, kinetic head minus actual kinetic energy or kinetic head divided by actual kinetic head gives the value of CR. Now that can be written like this. Kinetic head is nothing but V square by 2G. I have explained that earlier. So if you theoretical kinetic head means it is Vt square by 2G, where Vt is the theoretical velocity, minus actual kinetic head means Vs square by 2G, where V is the actual velocity, divided by Vs square by 2G. If you simplify this, you get something like 2G can be cancelled out, and here for this VA, I can put it as CV into Vt like this. So that means it is CV square minus into Vt square divided by CV square into Vt square. You can take Vt square common and you can cancel. So finally you will be getting it 1 by CV square minus 1. So that is the expression for coefficient of resistance. So that means in the case of a small discharging free sharp-ended orifice, actual velocity is given by Va is equal to Cv into root 2gh, and actual discharge is given by A into Va, where A is the area of jet vena contracta and Va is the actual velocity, and these are the different coefficients that can be defined for an orifice, and this is the relationship between them.